All right, welcome everyone. So, kind of our last lecture here, so our last bit of new material, and we're really going to tie in a lot of things today. So, we'll kind of go through our new material, and then I'll have a few announcements at the end just about kind of finals week and our exam today as we're kind of finishing up all our assessments. So I'll kind of make announcements about all of that at the end of the lecture today. So let's get into it. We're going to look at our last learning outcome, so IC4, and here we're going to actually see the definition of the definite integral using approximating rectangles and really Riemann sums. So, after this lecture, you should be able to kind of explain the definition of the definite integral and be able to calculate Riemann sums. And we're going to kind of start with this where we left off last time, which was talking about distance. All right. So, we have the distance problem, and we've kind of looked at this already, but we're going to look at it more in an applied sense. So let's see how to estimate the distance traveled by an object during a certain time period, provided that we know the velocity at certain moments in time. So we've seen how to do this if we know the velocity function in its entirety, but what about if we only know the velocity function at these brief little snapshots in time? So the idea for how to do this is if we know velocity is a constant, then distance is actually very easy to calculate. It's just velocity times time. So the idea is if we're interested in calculating the distance that we travel during a certain time period, so from A to B, for instance, what we're going to do is we're going to take that time period, that time interval, and let's write it as kind of as an interval here. And what we're going to do is we're going to slice this up into a whole bunch of tiny subintervals. So we're going to split this big time period from A to B up into many subintervals. So it might look something like this. And what we're going to do is for each of those little subintervals, these are little moments in time, little subintervals of time, what we're going to do is we're going to assume that we're traveling at a constant velocity on each of those subintervals. And so then to approximate the distance that we travel on each subinterval, we just calculate it with that formula. Distance is equal to our constant velocity on that subinterval times time. And so once we have all these little distances that we travel, so for each little subinterval that we do, we're going to have a distance that we travel during that time subinterval. And so to get the total distance, we're just going to add up it's going to be the sum of all those little tiny distances that we traveled. So during each of those little subintervals, we travel a little bit of a distance. So we're going to add up all those little distances together to give us the total distance that we traveled. So let's look at an example where we're going to do this. So let's suppose that we want to estimate the distance our car travels during a 30-second time interval. And to do this, we take speedometer readings every 5 seconds. So here, our time period is the interval of time from 0 to 30. And we're interested in how far we travel during that time period. And so let's represent that time period as an interval. And what we've done by taking those speedometer readings is effectively we've sliced up that time interval into many different little smaller subintervals. So something like that. So each of those little subintervals has the same width to it, basically. And so for each subinterval, what we're going to do is we're going to assume that we travel at a constant velocity during that small subinterval. So let's calculate the distance traveled on that first subinterval, which is from 0 to 5. So we're looking at this first subinterval here from 0 to 5. And we need to figure out, well, what constant velocity, we assume we're traveling at a constant velocity, and realistically we're not, but we're going to assume that we are. And so which velocity reading should we use? So for this example, we're going to use the initial velocity on that subinterval. Now you might use something different, and that's okay. But for this one, we're going to use the initial velocity. So if we're looking at the interval from 0 to 5, just that small subinterval, we're going to use the initial velocity on that subinterval, and so it would be the value for reading of 25. So for this interval here, we're going to assume, so this, in the end, this is going to be an estimate. It's not going to be an exact value because we don't know our velocity at every single moment in time. We only have these little snapshots. And so we're assuming on this interval from 0 to 5, we're assuming we're traveling at a velocity of 25 feet per second. And so we used our initial velocity, and sometimes we say we're using the left endpoint. So when we look at that interval from 0 to 5, we're using 0, the left endpoint, to figure out our velocity. All right, so on that subinterval from 0 to 5, we're assuming we're traveling at a constant velocity. So to figure out the distance, it's just the velocity that we're traveling at, 25 feet per second, times how long we actually are traveling during that subinterval. And so the amount of time for that subinterval it's 5 seconds long. So this is our velocity, and this is the length of our subinterval. It's the amount of time that we're traveling at that velocity. All right, so that's how far we travel, an estimate for how far we travel during that first subinterval from 0 to 5. Now let's go and calculate the distance for the second subinterval. And this one is from 5 to 10. And so we have a choice, which velocity reading should we use? And like we said, we're going to use the initial velocity for that subinterval. So in this case, we're going to look at the velocity at t equals 5, the left endpoint of our subinterval. And so our velocity at t equals 5 is 31, based on our chart there. So for that second subinterval, now we're in between 5 and 10, in between 5 and 10 seconds, we're assuming, for the purposes of these calculations, that during that time interval from 5 to 10, we're traveling at a constant velocity of 31 feet per second. And so to figure out the distance then that we travel during that time, we just take our velocity, which we're assuming to be constant. So we're traveling at 31 feet per second. Multiply that by how many seconds we actually travel. so 5 seconds. And that's our total distance during that subinterval. So again, this is our velocity, and this is the amount of time that we're traveling during that subinterval. So from 5 to 10, there's 5 seconds there. And we basically play this game over and over until we go through all of those subintervals. So when we're looking at this, how many subintervals are there going to be? Well, we looked at the first one, the second one. There's going to be a third, a fourth, a fifth, and a sixth. So there's going to be 6 subintervals where we do this calculation. So once we have all those, we just take all the results, add them together, and that gives us an estimate for how far we traveled in between 0 and 30. So let's finish it off. So our total distance and we'll write this as during that interval from 0 to 30 is going to be how far we traveled during that first subinterval, which was from 0 to 5, plus the distance in that second interval, which was from 5 to 10, plus the distance that we travel in the third one, which is from 10 to 15. And we just keep doing this. And so, let's write it all out. But we'll be thankful in a few minutes, because there is going to be a simpler way to write out where we have all these things that we're adding together. But call this character building. So we're just adding up all these distances over all these little subintervals. And then we stop once we get to that last subinterval, which goes from 25 to 30. All right, so how did we figure out the distance traveled during that first subinterval from 0 to 5? Well, we took the initial reading, which was 25, and we multiplied it by the length of the amount of time, the length of our subinterval, which was 5. Then for the second one, we took the initial reading there, which was 31, multiplied it by the amount of time in that subinterval, again 5 seconds. And so we just keep doing that for the third distance. So here our starting time for this subinterval is at t equals 10. So to find the velocity for that third subinterval, we're going to use 35. And again, there's 5 seconds in that third subinterval. Then we go to our next subinterval. We're using the left endpoint, so 15. That gives us that's how we look up our velocity reading. So we're going to use 43. So we're assuming our velocity is constant on that subinterval, 43 feet per second. And we're traveling for 5 seconds during that subinterval, so multiply it by 5. Then we go to our next one. We're using the left endpoint, our initial velocity. And so it's 20. Look up the velocity, it's 47. And we multiply by the amount of time, which is 5 seconds for that subinterval. And then finally we get to our last one, and we're using the left endpoint, our initial velocity, at t equals 25. So our velocity reading there is 46. And so we're going to travel at 46 feet per second times 5 seconds. And then just do all that arithmetic, and what we end up with is 1,135 feet. So that's the total distance, and I'll write that over here because that's an estimate for the total distance that we traveled during that 30-second time interval. Now, we want to be able to kind of simplify this notation down a little bit. And we want to be able to write it in function notation. So when we look at this 25 and this 31 and this 35 and so on, these velocity readings, these are really our function value. And so that 25, that was really our velocity at time 0. Same for the rest of these. Don't want to run out of room. So we'll keep writing that in a second. So 25 was really our velocity at time 0. 31 was really our velocity at time 5. So what does that 5 represent? Well, how we're going to write this, these 5s, this is the width of our subinterval, and we kind of consciously made the decision to take speedometer readings every 5 seconds. So we do these at very consistent increments in time. And so we're going to call that 5. That's really the kind of the increment that we're taking our readings in. And so to write this out, it's a bit of a mouthful here. It's a lot to write, even for just 6 subintervals here. But really what we're doing in calculating those distance, it's the velocity at time 0 times delta t. Then it's the velocity at time 5 times delta t. Then it's the velocity at times 10 times delta t. And we just keep doing that, and then add all the results together. So this is really kind of the behind the scenes of what we're doing with our numerical calculations here. And we're going to see how to kind of write this a little bit easier in a few minutes. So that's total distance. And so there's a question, why didn't we do the last interval? So when we do our subintervals, and maybe I'll mention this when we go over area, which we're going to do next. So I'll kind of address that question next when we talk about area. All right, so we've looked at distance problems before. We did that last time. In last lecture, we saw how to calculate distance, but we've also looked at how to calculate area. And so we have this kind of overlying problem that says, if we have an interval that we're interested in, is there a way to estimate the area under the curve, provided that we know the height of the curve at certain locations? And so we're going to go through a very similar setup here that we did for distance, but we're going to do it in the context of area. So the idea is, if we know our height is constant, then the area is very easy to calculate because it's just the area of a rectangle. So if our curve has constant height, then it really means we're talking about a rectangle, and rectangles are easy to calculate the area of. So if this was our rectangle, we have the width of our rectangle and we have the height of our rectangle, and so to get the area, it's just width times height. So if we have a curve and we're interested in finding or estimating the area under the curve over a certain interval, what we're going to do is we're going to let's say our interval is from A to B. what we're going to do is we're going to take that whole big interval from A to B, and we're going to slice it up into many tiny subintervals. And on each of those subintervals, even though our curve is, it's going to be curved, most likely, on each of those tiny little subintervals, we're going to assume that our curve has a constant height. So on each of these tiny little subintervals, we're going to assume that our curve has a constant height. And so we're really going to think of the area under the curve as a whole bunch of little rectangles that we're calculating the area of. So we have our big interval. We're going to slice it up into many little pieces. On each of those pieces, we're going to assume that we have a constant height. So then we can just calculate the area of the approximating rectangle, just width times height. And then once we have all those tiny little area calculations done, to get the total area, it's just going to be the sum of the area of all approximating rectangles. And we're going to try this out in an example. So let's see how this looks. Let's go to example 2. So we're given the approximating rectangles here, and we're going to use them to estimate the area under the graph of y equals f of x on the interval from 1 to 7. And here we're going to, you can see by the graph there, we're going to slice up that interval into 3 smaller subintervals. So our interval is from 1 to 7. And what we're going to do is we're going to break that apart into 3 smaller subintervals of equal width. So that means we're going to make a slice at 3 and then at 5. So 2 slices to get our subintervals. So we have our first subinterval, which is from 1 to 3. Then we have our second subinterval, which is from 3 to 5. And then we have our third subinterval, which is from 5 to 7. And so the idea here is on each of those subintervals, we're going to assume that our curve, even though our curve it's got some bumps in there, we're going to assume that our curve has a constant height on each of those individual subintervals. So when we look at this first subinterval from 1 to 3, the way we've drawn in our approximating rectangle here is using kind of the midpoint. So we've used kind of the halfway point between 1 and 3 as where we're going to estimate the height of our rectangle. And so it looks to be, based on that point, looks to be the height of that first rectangle is 1.6. So on that first subinterval, we're saying our curve is, has a constant height of 1.6. So to get the area for that first rectangle, it's going to be height times width. So what's the height of our rectangle? Well, we said it's 1.6. And why is it 1.6? Well, because we're reading off of this point here on our curve, and the y value is the height, 1.6. So that's our height. And we also need to know the width of our rectangle. And so the width of our rectangle is kind of the length of our subinterval from 1 to 3. And so the width there is 2 units. So we're going to multiply by the width of our subinterval, which is 2. And so you do the calculation there, we end up with 3.2. So the area for that first rectangle is 3.2 units, square units. Then we'd play the same game. We go to the area we go to our second rectangle there. And even though our function is curved, we're going to assume on that subinterval we have a constant height. So for our second interval, now we're in between 3 and 5, we're going to assume that we have a constant height, and the height there is the y value of our coordinate. So it looks to be 0.2. So for that second rectangle, it's 0.2, and then it's the same width. So we split everything up very kind of evenly. So each of these rectangles has the same width. So 2 in this case. So the height of our rectangle, the width of our rectangle, and do the multiplication, we get 0.4. So that tiny little rectangle there in the middle has an area of 0.4 units, square units. And so then to get the total area, you just keep doing this, but it's really the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle. And so we keep going. So the area for that first one was 1.6 times 2. Again, the 1.6 is the height. Area for that second rectangle was 0.2, and the width was 2, so 0.2 times 2. And for that last one, the third one, it's going to be the height of the rectangle is 2.5, and the width is 2. Again, the 2.5 is coming from our reading the graph, essentially. And so to get the total area, do the calculations there, and we should end up with 8.6. So the total area is approximately 8.6 square units. Now when we read off, again, when we start adding a whole bunch of things together, we want a notation that kind of simplifies. And so we're going to try to interpret this as function notation instead. So for instance, when we look at this 0.2, that's the height of that second rectangle. Really what this is our function value at x equals 4. So we're just reading off the graph there. And this times 2, it's the width of our subinterval. And we've done this so each of our subintervals has the same width. So we're going to call that delta x, just for shorthand. And so actually we can even adjust this function value a little bit more, kind of generalize it a little bit further. So we could actually say this is f of x2. It's our second known height. So another way to think of what we're doing here with this area calculation is we're taking our first known height, which we could write as f of x1 times delta x. Then we could take our second known height, which is would be f of x2, just our second known height. The subscript 2 just means it's the second one, times delta x. And then finally, our third known height, which we could write as f of x3, just the height of our third rectangle there, and times delta x. So this is really the notation that we want. It gives us a way to kind of generalize this or to go further. And so let me see. Did I answer? So when we, yeah, so there's a question. So when you're picking the, actually we'll get to it. So there's a question. When you're kind of picking the endpoints of the intervals, it looks like you miss one sometimes, and we'll see that. I thought we might be able to cover it during this area calculation one, but we're going to get to it in a few slides. So just hold on. And there was another question. In case you leave, the test for today is not going to include this material. So it's only the previous tested material. So all the questions from exams 1 through 6, that's what's going to be on the follow-up exam. So it's just your chance to retry any of those problems from exams 1 through 6. What we've done in IC Learning Outcomes IC1, IC2, IC3, IC4, what we're doing today and the past couple lectures, it's not going to be on today's exam. So today's exam, it's purely optional. It's only gonna, it's your chance to retry any of those old exam questions. So this new material is not going to be on the exam tonight. Might be on the final exam, but it's not going to be on the exam tonight. All right. So like I said, we want a notation to kind of simplify this process of just adding up a bunch of things. And the notation that we use is called sigma notation. And this is, we're going to think of it, it's just a big plus sign. It's a big addition sign. So this is our sigma here. And this really tells us to add. And what are we adding? Well, we're adding, it says a sub I. And I is an index number. Usually an integer. And so when we look at this, at the bottom of that sigma, there's this I equals 1, and that tells you what index number we're starting at. So in this case, we're starting at I equals 1. You don't have to start at I equals 1. Might start at something else. In most of the cases we're going to see, we're going to start at I equals 1. And then the number up here, this tells us where to stop. So where to end. In this case, I equals n. So when we see this sigma notation, sigma I equals 1 to n of a sub I, what it's really telling us to do is it says, okay, take a1, take a2, take a3, a4, a5, a6, a7, up to an, and then just add them all together. So it's really just a big addition sign where you repeatedly just add more and more things. So we can simplify in our distance example and our area example, we can use this sigma notation to simplify the writing down a little bit. So for our distance example, what did we do? Well, essentially what we were taking is we had our velocity at our first known velocity times delta t, then our second known velocity times delta t, and we kept doing that for 6 subintervals. So we got up to v, our last velocity there times delta t, v evaluated at t sub 6. And so to write this in sigma notation, we would write this as sigma I equals 1, not n. It's going to be 6 because we're adding up 6 kind of gadgets together. So we're starting at index 1 and going up to index value 6. And we're taking our velocity reading times delta t, the length of our time subinterval, and adding all those together. So delta t in this example was the width of each subinterval. Now in our area calculation, there we took our first known height times delta x, then we took our second known height times delta x, and then we took our third known height times delta x, added those together. If we were to write this in sigma notation, it would be sigma I equals 1 to 3. So we're adding up 3 gadgets there. And it would be our function value evaluated at xi times delta x, where we said delta x was the width, again, of each subinterval. So f of xi would be the height of our ith rectangle. So f of x1, that was the height of our first rectangle. F of x2, that's the height of our second rectangle. F of x3, the height of our third rectangle. So when we have a whole bunch of these things being added together, we can use this sigma notation to kind of simplify the writing a bit. And we give this a special name. We call it a Riemann sum. So when we take a function value times delta x, and we do this repeatedly and add them all together, we're calling this a Riemann sum. So, in sigma notation, it's sigma I equals 1 to n of f of xi times delta x. And this is equal to f of xi times delta x plus f of x2 times delta x. And we keep doing that up until we get to our last one, n. So plus f of xn times delta x. But we can really think of this, if we're thinking in terms of area, it's the height of our first rectangle times delta x. It's the height of our second rectangle times delta x. And we keep doing this for all of our little rectangles, and then we just add them all together. So when we have our subinterval, when we have our interval, usually we're talking about some interval from A to B. So in the context of area, we might be interested in finding the area under the curve from A to B. And so what we've done is we've said, let's take that big interval and let's break it up into many tiny little ones. All of the same width. And so delta x is the width of each of those smaller subintervals. And we make them so that they all have the same width. And so what we're going to do is for each of those subintervals, and let's kind of start with the first subinterval here, we want to pick a number out of that subinterval. So x1 star, we're going to pick a number in the first subinterval. So we have some control over what number we pick. So for our velocity, we had that interval from 0 to 5, and we picked 0 to give us our velocity reading. We could have done all those calculations and had picked 5. So we have some control usually over which number to pick out of that first subinterval. And then we go to our second subinterval, we pick a number out of there, and our third subinterval, our fourth, and we just try to be consistent with it. So normally what we pick is we pick the right endpoints of our subinterval, or all left endpoints, or all midpoints. So let's look at the case where we pick right endpoints. So let's say we have our little subinterval, and what we're going to do for each of those little subintervals is we're going to pick the right endpoint. So if we have kind of our whole number line here from A to B, and let's say we have kind of a few subintervals here, we're going to pick for our first subinterval, we're going to pick not A, we're going to pick the one next to it. So x1 star is going to be A plus delta x. And so what n represents here, n represents the number of subintervals that we have. And so that's how many points we're going to be picking. So when we look at our subintervals, for each subinterval that we have, we're going to pick one number out of that subinterval. And so if we, in the context of doing right endpoints, for that first subinterval, we're going to pick the right endpoint. And it turns out to be A plus delta x. And then to get the rest of them, our second point, our third point, and so on, we just add delta x. So it becomes a very nice iterative process. Once you have your first endpoint, you just kind of add copies of delta x until you get to your last point, xn star. And so if we kept picking right endpoints, eventually we get to our B value. And so these would be the points that we're using to find the height of our rectangle, or the velocity of, for our distance problem. Now we could use left endpoints. So if we have our subinterval, we could use the left endpoint. And so if we're looking from A to B, we slice this up. A little example here, let's break it up into 5 subintervals. And so if we're going to use the left endpoint, for our first subinterval there, for using the left endpoint, we're going to use A. So for left endpoints, x1 star is going to be A. And then to get the rest of our left endpoints, we're going to just keep adding delta x's. So for our next we're just going to add delta x. And so ultimately what this does is it gives us, this would be the endpoint for our second subinterval. This would be the point that we choose for our third one, our fourth one, and our fifth one here. And so notice that there's always this kind of relationship where when we slice up our interval, we're always going to have one kind of slice that we don't use. So if we're using our right endpoints, we're not using directly at A. If we're using our left endpoints, we're not using the slice at B. So that's just because n represents the number of subintervals, and we're only picking n points. And then the last one we sometimes use, and this one tends to give us the best estimate, is midpoints. So let's say we have our interval from A to B. We slice this up. And for midpoints, we pick the halfway point, halfway in between our the left and the right. So for our first subinterval here, we would be picking the halfway point. And so this would be A, and it's the midpoint, so it would be plus delta x over 2, halfway. And so to get the rest of your midpoints, so here's our second midpoint that we would want to use, our third midpoint, our fourth, and our fifth. So for each subinterval, we're only picking 1 point out of that subinterval. So we have, in this little diagram here, we had 5 subintervals. We're picking 5 points. So once you have your first midpoint, though, then just like the other ones, it's easy to figure out the rest. You just add delta x. So to get our third midpoint, you just add delta x. You just keep adding delta x's until you get to your last subinterval. So we're going to see how to use these right or left or midpoints in Riemann sum calculations in a second. But why this Riemann sum notation is helpful is because it's going to allow us to kind of generalize this for large n values. And that's the whole goal with this, is if we're only using 3 rectangles, it's not going to be a very good approximation. And so to get a better approximation, what we want to do is we want to slice our interval up into smaller and smaller subintervals. We want to use more subintervals. They're just going to have smaller widths. And so what we see is as the approximating rectangles, as n increases, so as the number of rectangles, essentially, or another way to think of it, it's the number of rectangles. As the number of rectangles increases, they're going to be thinner and thinner. We're going to have more of them, but they're going to be thinner and thinner. So overall, though, the approximating rectangles better represent the region under the graph. And so what we expect then is that our area calculation, we're estimating with those areas of those rectangles, is going to get better and better as well. And so here's a little example, same graph that we were looking at. This has 15 rectangles. And so if we wanted the area, an approximation for the area under the curve, we would do a Riemann sum. So it'd be the sum from I equals 1 to 15, and it would be the height times delta x. So our function value gives us the height of each of those rectangles, and delta x is the common width. And so what happens is as n increases, as we use more and more rectangles, it's going to give us a better and better approximation. And so the way that we kind of look at what happens as n increases is to do the limit. And so we're going to do the limit as n goes to infinity of this general Riemann sum, where n is going to infinity. N is the number of rectangles that we use. And so the limit as n goes to infinity would give us the exact area under the curve. So this is, the Riemann sum is just the sum of the areas of our rectangles. When we do the limit, though, of that as n goes to infinity, we're going to get the exact area in this case. So hopefully this works. Let's see a little animation. And all right, so here's our graph. And we're using one rectangle to approximate the region under the curve, which is not very good. So we can do better than that. So let's increase this. And all right, so there we're using 14 rectangles. It's looking a little bit better. And we can increase this. And as we increase the number of rectangles, it's looking pretty good. And there we have 100 rectangles. We've broken up that interval from 1 to 7 into 100 little pieces. And we have rectangles for each of those little pieces. And that looks pretty close to what we would expect for the region under the graph. And so the idea is, as we use more and more rectangles, as n goes to infinity, we get a much better estimate for the area under the graph. And so let's just see that one more time. So we start with n equals 1, not too good. What did we do? We did n equals, I don't know if I can get there. We did n equals 3. Easy to do by hand, but really we're interested in what happens when we move this out to 100 or more, beyond. N goes to infinity. We get a pretty good approximation. And so this is going to lead us to our definition for the definite integral. So the definite integral is of some function f from a to b. It's the limit as n goes to infinity of the summation from I equals 1 to n of f of xi times delta x. And this definite integral exists provided that the limit exists and is the same for all of those sample points that we might choose, right endpoints, left points, midpoints, maybe something different. But for this definite integral to exist, the limit has to exist, and it doesn't matter which endpoints we use, left, right, midpoint, something else. And so if the limit does exist, then we say our function f is integrable over that interval from a to b. So just a reminder on some of the notation here. First of all, the summation from I equals 1 to n of f of xi star times delta x, that's our Riemann sum. Delta x is the width of our subintervals, and so we're interested in our big interval, which is from a to b. N is the number of subintervals, so it's the number of rectangles that we're using, essentially. And delta x, then, is the width of our subintervals. So the way we calculate delta x usually is we want all of those subintervals to have the same width. We want all of our rectangles to have the same width. So delta x is equal to b minus a over n. It's the length of our big interval, and then we cut it up into n smaller intervals. So the width with delta x is b minus a over n. And then we use this notation xi star. This is what we call our sample points. And this is what we generally have some control over. We have some control over, well, what points do we want to pick? Do we want to pick the right endpoints, the left endpoints, the midpoints? Those are the most common ones that we use. You might pick something different. Those are the most common, though. And usually the midpoints are going to give us the best approximation out of those three. All right, so let's just work with this definition a little bit because there's a lot going on here. And the first question is, well, this seems complicated. And it is. So calculating the limit of a Riemann sum is as the number of subintervals increases is a very tricky thing to do. And in most cases, it's not something that we do directly. So we know how to calculate a definite integral. We have the fundamental theorem of calculus for that, which, it's still, there's still some work there, but it's not as difficult as, all right, let's add all these things together and then take the limit as we add more things together. So this definition is something that's very difficult to work with directly. But it turns out that and in a lot of cases, there's functions out there where we can't do the definite integral because this limit does not exist. So that's something just to be aware is not every function can be integrated. We'll see that in Calc 2. But it turns out a lot of the more common functions that we work with, they can be integrated, which is nice. So we have this result that says if our function is continuous on that closed interval from a to b, or we can even relax that a little bit. It can have a finite number of jump discontinuities. So it's continuous and then it has some jumps, but for the most part it's continuous. Then that function is integrable, and we can actually calculate the definite integral. So what this theorem says is we can integrate all functions that, one, are either continuous on that closed interval, or kind of like piecewise functions where there might be a couple breaks in our piecewise function. Those are okay as well. So they're continuous on the closed interval, but we might have a few kind of breaks or jumps in our graph, and that's okay. So except for a finite number of jump discontinuities. Infinite jumps, infinite discontinuities, those aren't good. So that's where things become an issue. So yeah, I think I have too many T's in there. So just to remember, back to our way back, what's a continuous function or what's a jump discontinuity? Those are things where we might have so that might be like our function where there's a little break, but it's not like an infinite jump where we have a vertical asymptote or anything like that. So that would be an example of a jump discontinuity. Those functions are okay as well, provided there's only a finite number. So this definition is very difficult to use directly. We don't normally calculate definite integrals by doing the limit as n goes to infinity of those Riemann sums. We have the fundamental theorem of calculus, which lets us calculate these definite integrals. But really where this comes in, these Riemann sums, this is more of a numerical type calculation. This is how you would calculate the definite integral numerically. But let's work with that definition a little bit for the notation. So in example 3, we're going to write this limit as an integral on the interval from 0 to pi. And so a lot of the notation that we use for our definite integral it's kind of motivated by that sigma notation. So when we see this limit of this sigma here, the integral kind of smooths things out. And so imagine taking that summation sign and just kind of smoothing it out a bit. That's our integral sign. The dx that we normally have in our integral, Well, that's our delta x. And then the function that we're integrating, well, that's the height of our rectangles. So in this case, it would be x cubed plus x times sine x. And for our definite integral, we are normally interested, we have upper and lower limits, and those come from our interval. So looking at our interval here, we're 0 to pi. So that tells us a is equal to 0, b is equal to pi. So our limits of integration then would be from 0 to pi. And so really what we're doing with a definite integral is we're taking up all these tiny little rectangles, calculating the area, and then adding them together. Let's do one more example. We're going to do a Riemann sum. So we're going to evaluate the Riemann sum for this function f, which is equal to x cubed minus 6x on the interval from 0 to 3. And we're going to take our sample points to be the right endpoints. And we're going to use 6 rectangles here, essentially. All right, so let's see how the Riemann sum calculation would work. So let's start step 1. Let's figure out the width of each of our rectangles. And this is delta x. And what we're going to do is we're going to take our interval from 0 to 3, and we're going to slice that up into 6 pieces. So delta x is b minus a divided by n, where b and a are the endpoints, and n is the number of rectangles. And so if we do this, we get 1/2 or 0.5. So we have this interval from 0 to 3. And what we're going to do is we're going to break this up into 6 pieces. So in order to do that, we're going to make 5 cuts. And hopefully I can get these. Nope. It's hard to get them spaced out ahead of time to make them look like the same width. So we're going from 0 to 3. We're making 5 cuts. And the reason why we do that is because that's going to produce our 6 subintervals. All right. So those are our 6 subintervals. And what we're going to do is for each subinterval, we're going to pick a point out of that subinterval. That's our sample point. And what we're going to do is we're going to use the right endpoints. All right, so for our first subinterval, we're going to pick a point out of that one. We're going to call it x1 star. And we're using the right endpoint. So if we look at that first subinterval, the right endpoint is there. So what is this x1 value? Well, it's going to be a plus delta x. So that's where we start with our right endpoints. So in our case, a is 0 and delta x is 0.5. So the first location we're going to use, the first sample point we're going to use is x1 star. It's going to be 0.5. So we're going to use that x value to figure out our first rectangle. So let's draw in our rectangle. And so we're starting at 0.5, and that's where we're going to use that location to draw in our first rectangle. So we find 0.5, and we go until we hit the curve, and that gives us our first rectangle. So we're using that first sample point to get that first rectangle. All right, let's get our second rectangle. So to do that, we're going to use our next right endpoint. So we go to our second subinterval, and we're going to use the right endpoint there. And so the easy way to find our next endpoint is to just take our previous one and add in delta x. So our previous endpoint was 0.5. We're just going to add in another 0.5. That's delta x. So we get 1. So our next location that we're going to use to figure out our rectangle is x equals 1. So we find that on our x-axis. And then we go until we hit the curve. And that gives us the height of our next approximating rectangle. So there's our next rectangle. And then we just keep playing the game. So we want for our third subinterval, we want to pick a point. We're going to use the right endpoint. So for our third subinterval, there's our third subinterval, and we're going to pick the right endpoint. So we're going to pick over here. But really how we calculate that is we just take our previous sample point and just add in delta x. So you can just iterate this. So we take 1 plus delta x, which is 1.5. We get 1.5. So that's our next location that we go to. So we find 1.5 on our x-axis, and then we read up or down, depending on where our curve is, until we hit the curve, and that gives us the height for our third rectangle. So we have our third rectangle there, and we just keep doing this. So we have 3 more to go. So to get our next location, what are we going to do? Just add in another delta x. So our previous one was 1.5, and so when we add 0.5 to that, we're going to get 2. So we go to 2 on our x-axis there. We're going to draw in our rectangle. So we go down until we hit the curve. That gives us the height for our fourth rectangle. And there we go. There's our fourth rectangle. Our fifth one, we're going to add in delta x, another delta x. So we were at 2. Now we're going to be at 2.5. So we find 2.5 on the x-axis, and it looks to be that our curve is now slightly above. So our rectangle, our fifth rectangle, is going to be slightly above the x-axis. And we have one more. So that's our fifth rectangle. We need our sixth one. So to get our height, we're going to figure out x6 star, and we just take our previous value and add in another delta x. So our previous value was 2.5. We add 0.5 to that, we get 3. So we find 3 on our x-axis. We read up until we hit the curve, and that gives us our last rectangle. And so what we're going to do then is we're going to find the area of each of those rectangles, essentially, and add them all together. Yeah, that actually looked pretty good. All right. So we have these 6 rectangles that we've drawn in. And so to get the Riemann sum, we're going to be starting at I equals 1 and going up to 6 because we're using 6 rectangles. And to kind of help us out here, we can factor off that delta x. So when you're writing this out, it might help to write out or to factor off that delta x. And there's a computational benefit to this as well. You're doing less multiplication. So, if we were going to write this out, we would take our function and plug in our first x value that we found, which was 0.5. Then we're going to take our second x value, plug that into our function. So 1. And then 1.5 was the third one we found. Then 2 was the fourth. 2.5 was our fifth one. and then 3 was our 6th one. And then we're going to factor off the delta x. So we're going to add up all those function values and multiply by delta x. We could just leave the delta x multiplied in perfectly fine, but it helps computationally just to factor that off, put it at the end. And so then it just becomes a number crunching. So take 0.5, plug it into the function, and what we end up with is negative 2.875. Take the second value, and what we end up with is negative 5, and then negative 5.625, and then negative 4. And then once our rectangles go above the x-axis, that's where we start getting our positive values. So 0.625 positive, and then finally 9 for our last height there. And then delta x we calculated was 0.5. So we do all the arithmetic there, and what we end up with is negative 3.9375. And why it's negative? Well, some of those rectangles were below the x-axis, so those are giving us the negative values. And so sometimes we call this, we might call this value R6 for R because we used the right endpoints, and 6 because we used 6 rectangles. So if we were doing left endpoints, we might end up calling this L6. And if we were using midpoints, we might call it M6. And a Riemann sum can be negative, just like we saw definite integrals can be negative. And what that means is, well, we have more, the rectangles that fall below our x-axis there there's more of them, and they have more area than those 2 rectangles at the end that are sitting above the x-axis. And so if we were to kind of repeat this process for larger and larger n values, what we would see is that as n increases, what we're doing with all these tiny little rectangles is this is our Riemann sum. It's the height of each rectangle times delta x, the width of each rectangle, and we might have like n of them in general. In this diagram here, we have 25 little rectangles there. And really what this Riemann sum is calculating is it's calculating the area of those rectangles that are above the x-axis minus the area of those rectangles that are below the x-axis. And as we let n increase, as n goes to infinity, we're getting our limit definition of the definite integral. And this is exactly how we defined our definite integral. So as we use more and more rectangles, as n goes to infinity, we're going to be using more of them. They're going to be thinner, but they give us a better approximation for what our region looks like. And so it's giving us, ultimately, the net area. It's the area that lies above the x-axis minus the area that lies below the x-axis. So let's see a little illustration here. So here's our region, and we're using one rectangle, so it's not very good. And we're using right endpoints, right endpoint here. We did, what did we do? We did, let me see if I can get it. Yeah, too tiny. We did something close. There's 8 rectangles. But as n gets larger and larger, we see that the region becomes looks much closer to what we expect for the region between our curve and the x-axis. So here's 100 rectangles. We've taken that interval from 0 to 3 and we've sliced it up into 100 pieces, and we have our rectangles there, all right endpoint rectangles, and our region that they're covering up looks to be that region under the graph and between the x-axis that we've kind of looked at in our area calculations. And so what we're seeing here, all those little rectangles that fit below the x-axis, they're contributing a negative amount because they're below, and all those rectangles that are above, they're going to contribute a positive amount because they're above. And so what we're getting when we do the definite integral is ultimately we're taking those rectangles that are above and we're subtracting off the area of those rectangles that are below. So you can see as n increases, as we take the limit as n goes to infinity, the region looks more and more like the region under the graph. So we'll be talking about Riemann sums in Calc 2, so don't you worry. But we're going to stop there. So that's where we're going to end 141. So it kind of brings together a lot of the concepts of limits and definite integration that we've been talking about. In practice, it's very difficult to calculate the definite integral directly. Riemann sums are not too bad. That's more of just a numerical calculation. Gets a little boring, just adding a whole bunch of things together, but it's not too bad. It's something that a computer can do very well. But to actually prove a definite integral using that limit definition is very difficult. So the fundamental theorem of calculus that we've been working with so far simplifies this process considerably for those nice functions. All right. So that's it on the new material. Just a few announcements before we get going today. So tonight we have follow-up exam 6. So that's just covering old material. What you've seen on exam 1, exam 2, exam 3, exam 4, exam 6. So what we did today is not going to be on the exam tonight. It's just those old questions from the previous exams, so you have another opportunity to get a mastery check for those learning outcomes. So that's tonight. It's an hour-long exam. All the old homework assignments are reopened. So anything that you didn't have complete, you have until Monday at 11:59 p.m. to finish any of those old homework assignments. Feel free to ask questions on our course website. I still have office hours tomorrow in case you have any questions about the homework. Now for finals week, I will have office hours and I will be scheduling a review session for sometime probably on Tuesday. So I'll make an announcement about that. But essentially what we'll cover in the review session is I'm going to, after the follow-up exam tonight, once everyone's completed it, I'll post that follow-up exam. So that'll give you kind of some extra material to study from. And then during the review session, we'll kind of just go through all the questions on the follow-up exam and use that as kind of branching points to kind of review the different topics in the course. So that's what I'm planning for next week. I'll make a more specific announcement on when. So just kind of check your email, check the course website. And then our final exam is on Thursday at 11:45 a.m. So just make sure you don't have a conflict with another final exam. If you do, you should have received a link for a Google form that you should fill out, just indicating that you have a conflict. So make sure you fill that out. And then let me know if you have any questions. So I'll see everyone. Well, I won't see everyone, but I'll see some people tonight for the follow-up exam. So if you have mastery on all the questions, you don't have to come for the exam. And then I'll make more announcements, like I said, about when the review session will be next week and when my office hours will be next week. I do have office hours this week on Friday. And then you can always ask questions on the course website. And then, yeah, I think that's it. So follow-up exam tonight. All the homework assignments are reopened. Final exam next Thursday. We'll have a review session probably on Tuesday. I'll make an announcement about specifically when. Oh yeah, and then the last 4 sections, what we just finished up today, IC1, IC2, IC3, IC4. There are homework assignments for those. Those are due Wednesday. Those weren't tested on a recitation exam. So the way you earn your mastery check for those 4 learning outcomes is you only have to complete the homework. These topics still might show up on the final exam, but we didn't get to them for a recitation exam. So the way you earn your mastery check for those 4 learning outcomes only, just do the homework. All right. So we'll stop there. Went over a couple minutes, but it's worth it just talking about what to expect. If you have any questions about the final exam or anything, about the logistics of the final exam, let me know. I'll be making, more announcements about the final, as we get closer. So just kind of stay close to your email and stay close to our course website just for those updates. All right. So good luck studying today. I know you probably have a lot of other courses that are finishing up at the same time. So good luck with all of those. I'll see you tonight for the follow-up exam. And then, this isn't the last time. So next week we'll have a review session. So we'll see everyone then as well. So bye-bye.